All right, so you know how when you have your morning coffee, it always seems to cool down?
Yeah.
It never like spontaneously heats back up.
Right.
And it's not just a quirk of the kitchen. This actually points to something much deeper, this principle that governs the entire universe, the arrow of time.
Yeah.
And so today we're going to tackle this head on. We're going to be exploring thermodynamics to understand how the science behind energy and heat and their transformations helps us kind of unravel this whole mystery of time's direction.
It's interesting because this idea that there's this arrow of time, it's not just some kind of abstract philosophical idea. It's actually rooted in some concrete laws of physics.
Really?
And specifically in a field called thermodynamics, which you've brought up.
So we're talking about a deep dive into thermodynamics, specifically the second law, to see how it connects to this idea that time only moves forward.
Yeah. And get ready to explore some pretty mind-boggling concepts.
Yeah.
We're talking about entropy and the potential for the universe to reach a state of heat death.
Heat death.
And we'll even talk about how those massive cosmic events, like the formation of stars and black holes, how those are all tied back to these fundamental laws.
Okay. That sounds pretty intense, but before we get ahead of ourselves, what exactly is thermodynamics?
So you can think of thermodynamics as the study of energy, heat, and how they transform within a system.
Okay.
It's kind of like the physics of energy flow.
So like a cosmic accounting system for how energy flows in the universe?
You could think of it that way. It really took off during the 19th century, spurred by those massive steam engines popping up everywhere.
Yeah.
Figuring out how to make them more efficient was a huge deal, and that led to some discoveries about energy itself.
Wow. So the quest for a better engine led to some universal truth about how energy works.
It did. And from all of that research came the 4 laws of thermodynamics.
Okay.
These are like the fundamental rules that govern how energy plays out on the cosmic stage.
So what are these 4 laws all about?
Well, we've got the Zeroff law.
Right?
This one's all about systems reaching a state of thermal equilibrium. Okay. You know, like when your coffee and the room it's sitting in, they reach the same temperature.
Right.
They've reached equilibrium, and there's no more net flow of heat between them.
Oh, interesting. So it's about things kind of balancing out in terms of their temperature?
Yeah.
What about the first law?
So the first law is probably the most familiar. It's the conservation of energy.
Oh, right.
Energy can't be created or destroyed, only transformed from one form to another.
Oh, right. So it's like how the chemical energy stored in gasoline gets converted into kinetic energy to move a car.
Yeah.
But the total amount of energy in the system remains the same.
Precisely. Now, for the second law, this is where things get really interesting. And this is really the key to understanding the arrow of time. This law states that the entropy of an isolated system always increases over time.
Entropy. That's a word that I hear tossed around a lot,
Yeah.
but I'm not always sure I fully grasp it. Can you break that down for us?
Okay. So imagine you have a perfectly arranged deck of cards. That's a state of low entropy, high degree of order. Now, you shuffle that deck.
All right.
The cards are all mixed up, it's more disordered, and therefore has higher entropy.
Okay.
So the second law basically states that things in the universe have this natural tendency to go from order to disorder over time.
So is that why I'm constantly battling clutter in my house? The universe is like working against me.
Well, maybe not working against you, but you're definitely going up against a fundamental law of nature there.
Mm-hmm.
Think about ice melting in a warm room. It naturally melts and spreads out, it becomes more disordered, but you never see it spontaneously refreeze and like gather itself back into a neat little ice cube.
Yeah.
Or think about your coffee getting cold. That heat energy is spreading out into the room and increasing the overall entropy of the system.
Right. So the fact that we can't like unspill milk or unbreak an egg, is that all because of this concept of entropy always increasing?
Exactly. Most processes in nature are irreversible because of this ever-increasing entropy. To reverse them, you'd have to like rearrange things at a microscopic level. Wow.
With an insane amount of precision, something that is incredibly improbable, bordering on impossible.
So this irreversibility, this one-way street that entropy creates, that's what gives time its direction.
That's the crux of it.
It's like a built-in arrow for time in the universe.
And it's fascinating because most fundamental laws of physics don't care about the direction of time. They work the same forwards or backward. It's the second law, this concept of increasing entropy, that creates this arrow for the macroscopic world that we experience.
Wow, that is mind-blowing.
Yeah.
But how does all of this high-level physics translate to the real world? Like, what are some examples of thermodynamics in action that we might encounter in our everyday lives.
Okay. Well, let's start with something you probably use every day.
Okay.
Your refrigerator.
Okay.
Now, at first glance, it seems like a refrigerator defies the second law.
Really?
Because it's making things colder inside, creating this order, right?
Right. So is my refrigerator like an entropy rebel fighting against the universe's tendency towards disorder? In a way, yes, but it's not actually breaking the second law. A refrigerator uses work, which is an input of energy, to move heat against its natural flow. You get that lovely cold food and drinks inside at the cost of generating more disorder outside, releasing that heat into the environment.
So it's like a trade-off. You can't create order in one place without generating disorder somewhere else.
Precisely. And another great example is an engine.
Okay.
It's designed to convert heat into work, but there are limits to its efficiency because of that second law.
Okay.
Some energy always gets lost as unusable heat, increasing that overall entropy in the process.
So it sounds like the second law is this ever-present force that limits what we can achieve, kind of a cosmic killjoy.
Well, I'd say it's more like a fundamental principle that governs how energy behaves, but these same thermodynamic principles are also at play in the grand scheme of things, dictating the formation of stars and even black holes.
Wait, hold on. So we're talking about cosmic scale thermodynamics now.
We are.
Stars and black holes operate under the same rules as my refrigerator.
They do. It just shows how universal these laws are, governing everything from the tiniest atoms to the most massive celestial objects.
Wow.
We're all dancing to the tune of thermodynamics.
So last time, we were talking about how the same thermodynamic principles that govern my fridge are also at play in the formation of stars and black holes. It's incredible to think that those massive cosmic events are following the same rules of the game as my kitchen appliances.
It really highlights just how universal these laws are. But this leads us to an even bigger question.
No.
If thermodynamics governs those massive objects, does it also have something to say about the ultimate fate of the entire universe?
That's a great question. I mean, if entropy is always increasing, does that mean the universe is headed toward some sort of ultimate state of disorder?
That brings us to one of the most fascinating and perhaps unsettling ideas in cosmology, the concept of heat death.
Heat death. That sounds pretty ominous. What exactly does that mean?
Well, remember how the second law dictates that entropy always increases? If we project that out to the entire universe over incredibly vast timescales, what we get is a picture of the universe slowly spreading out, cooling down as its entropy increases. Eventually, we reach a point where everything is so spread out and uniform that there are no more usable energy gradients left.
So it's like everything in the universe eventually reaches a lukewarm temperature. No more fiery stars, no more swirling galaxies, just a bland, homogeneous cosmic soup.
Yeah, that's the general idea, though. It's a process that would unfold over timescales that are almost impossible for us to even grasp. This state of maximum entropy where everything is spread out and nothing much happens is what's referred to as heat death. It's the ultimate winding down of the universe driven by that relentless increase in entropy.
Wow, it's a pretty bleak picture.
Yeah.
It kind of makes you wonder if everything is eventually going to end up like that. What's the point of it all?
Well, that's where we enter the realm of philosophy. This whole idea of entropy and the potential for heat death raises some pretty deep questions about the nature of reality, the meaning of time, and our place in this grand cosmic drama.
It certainly does. But before we get too lost in an existential crisis, I have to ask, are there any alternative perspectives on this heat death idea? Is it a certainty, or are there other possibilities?
Well, some physicists propose that the universe might not be a completely closed system. There might be ways for it to exchange energy or information with other universes or even realms that we don't yet understand. These exchanges could potentially prevent it from ever reaching a true state of heat death.
So we might be part of a much grander interconnected cosmos than we currently imagine, and that could change the whole heat death game.
It's a possibility. No, it is very speculative, but it does introduce some really interesting ways to think about how we might escape that seemingly inevitable slide into maximum entropy.
Okay, that's a little bit reassuring. But this whole discussion about entropy and time's arrow makes me wonder about something else. If disorder is the natural tendency, how did the universe start in such a low entropy state in the first place? It seems counterintuitive.
That's a question that has puzzled scientists and philosophers for ages. If things naturally tend towards disorder, how did everything begin in such an incredibly ordered state? One prevailing idea is what's called the past hypothesis, which suggests that the universe simply began in a highly ordered state for reasons we don't yet understand.
So are we essentially saying, well, it just started that way and we don't know why? Is there any scientific basis for this past hypothesis, or is it just a starting assumption?
It's one of the biggest mysteries in cosmology, and it's a fundamental assumption that underlies a lot of our current understanding. There are different theories and hypotheses out there drawing from areas like quantum mechanics and string theory, but no definitive answers just yet.
It sounds like we're bumping up against the limits of what we currently know about the universe. It's incredible how these seemingly simple observations about heat and energy lead to such profound questions about the nature of reality itself.
It really is. And the implications of these thermodynamic principles go even further. They even make us question the very nature of life itself.
That's right. It seems paradoxical that life, with all its order and complexity, can exist in a universe governed by this principle of increasing entropy. It feels like life is defying the second law. How does that work?
It's a great observation. It does seem like life is thumbing its nose at entropy by creating all this amazing complexity and order. But here's the key. Living organisms don't actually defy the second law. They actually increase the entropy of their surroundings in order to maintain their internal order.
So are you saying that life forms are like little entropy manipulators finding loopholes in the second law?
In essence, yes. They take in energy and matter from their environment, use it to build and maintain their complex structures, and then release waste products back into the environment. It's a delicate dance, but life finds a way to create pockets of amazing complexity while still contributing to the overall increase in entropy.
It's remarkable how life manages to thread that needle. But you mentioned earlier that the implications of thermodynamics go even further. What else is there?
Well, there's a fascinating connection between entropy and information theory.
Okay, remind me. How does information theory fit into this whole picture of heat, energy, and entropy? It feels like we're jumping between different worlds here.
It might seem like a leap, but there's a surprising connection between entropy with its concepts of disorder and randomness and the amount of information needed to describe something.
So if I have a messy room, it has high entropy and also requires more information to describe it. Like I need a detailed inventory to locate anything in all that chaos.
Exactly. Think about a library where all the books are randomly scattered on the floor. To describe where each book is, you'd need a massive amount of information, a detailed catalog. But if those books are neatly organized on shelves, the amount of information needed to describe the library state is much smaller. The more order there is, the less information you need.
I see. So entropy in the physical world, like a messy room or a chaotic library, corresponds to a larger amount of information required to describe its state. It's like the universe is playing this giant information game, and entropy dictates the rules.
That's a great analogy. And this connection between entropy and information has some really profound implications, especially when we start thinking about computers and computation.
Now, this is where I start to get a little lost. How do computers and information processing tie into the laws of thermodynamics? It seems like two completely separate worlds.
It might seem that way, but remember that every computation, every piece of information processed involves energy transformations. Even something as simple as flipping a bit from 0 to 1 in a computer's memory requires a minuscule amount of energy.
So even our digital world, with its seemingly abstract and intangible information, is still bound by the laws of physics and thermodynamics.
Absolutely. There's no escaping those fundamental laws, even in the virtual realm. And recognizing this has given rise to a fascinating field of study called the thermodynamics of computation.
Okay, thermodynamics of computation. That sounds interesting. What's the gist of it?
One of the most mind-blowing implications is that there may be fundamental limits to how efficient we can make computers, limits imposed by the second law of thermodynamics. Every computation generates a tiny bit of heat, a tiny increase in entropy. Even though it's incredibly small, this heat dissipation places a theoretical limit on how much computation can be done with a given amount of energy.
So you're saying that even though our computers seem to get faster and more powerful all the time, there's a limit to how efficient they can ultimately be. The second law is putting the brakes on our technological progress.
In a sense, yes. It really underscores the interconnectedness of everything in the universe. We may build these amazing computers, but they're ultimately subject to the same thermodynamic constraints as stars and black holes.
That's a humbling thought. But it also makes me wonder, are there any ways around these limits? Could we find ways to compute without generating heat and increasing entropy?
That's a question at the forefront of research in areas like quantum computing and reversible computing. These are fields that explore whether it's possible to develop new types of computers that could operate much more efficiently, potentially sidestepping some of those thermodynamic limitations.
That's fascinating. So there's hope that we might be able to break free from those thermodynamic shackles. What other mind-boggling ideas are being explored in this realm of thermodynamics and computation?
Well, one of the most radical ideas is that the universe itself could be viewed as a giant information processing system. Some physicists propose that the universe might be like a vast computer constantly processing information and evolving its state based on the laws of physics.
Hold on, the universe as a giant computer. Is that a serious scientific proposition, or are we in science fiction territory now?
It is definitely a mind-bending and speculative idea. However, it's gaining traction amongst some physicists and cosmologists. The idea stems from the growing recognition that information may be just as fundamental to the fabric of reality as energy and matter.
So those bits and bytes in our computers might be a reflection of something much deeper about the structure of the universe itself. We're just mimicking what the universe has been doing all along.
That's the gist of it. It's a concept that, while highly speculative, could completely revolutionize our understanding of the cosmos and our place within it. It really pushes the boundaries of what we consider possible.
It certainly does. It feels like we've gone from discussing messy rooms and refrigerators to contemplating the universe as a giant information processor.
And it all comes back to those fundamental laws of thermodynamics. Those laws aren't just about heat and energy. They're about information order and the very fabric of reality itself.
Last time we were venturing into some pretty mind-blowing territory, talking about the universe as a giant information processor.
Yeah.
It's hard to wrap my head around the idea that those tiny bits and bytes in our computers might be reflecting something so fundamental about the nature of reality itself.
It's definitely a paradigm shift, but it highlights how our understanding of information is becoming increasingly intertwined with our understanding of physics and the universe.
So let's unpack this a bit more. We talked about entropy as a measure of disorder, and also as the amount of information needed to describe a system. How does that connect to this idea of the universe as a giant computer?
Well, if we think of the universe as this system that's constantly evolving according to the laws of physics,
Right.
we can also think of it as constantly processing information. Each interaction between particles, every event that unfolds, can be seen as a kind of computation, a transformation of information.
So every star that explodes, every galaxy that collides, it's all just information being processed on this cosmic scale.
In a sense, yes. And this perspective leads to some really fascinating questions about the nature of reality. Like, for example, if the universe is processing information, what is the nature of that information?
Right.
What are the fundamental units of information in the universe?
It makes you wonder if there's some sort of cosmic code underlying everything, like a set of instructions that governs how the universe operates.
That's an idea that some physicists are actively exploring. They're looking for a deeper level of reality where information might be the primary ingredient and where the laws of physics emerge from how this information is processed.
Whoa, that's getting into some serious matrix level stuff. But if the universe is this giant computer, does it have a purpose? Is it computing something specific, or is it just running its program without any particular goal in mind?
That's a deeply philosophical question, and there's no easy answer. Some might argue that the universe simply is, that it exists without any inherent purpose. Others might propose that the universe is constantly evolving and processing information to reach some ultimate state, though what that state might be is anyone's guess.
Right. It's like we're asking if there's a programmer behind the universe, some grand intelligence that set it all in motion.
Yeah. And that question has occupied theologians and philosophers for centuries. But from a scientific perspective, we're still far from understanding if there's a deeper meaning or purpose behind the universe's computational processes.
Okay, so we're diving deep into the philosophical implications here. But let's bring it back to something a little more concrete. You mentioned earlier that there are potential limits to computation imposed by the second law. Does this idea of the universe as a computer change how we think about those limits?
It certainly adds another layer of complexity. If the universe itself is bound by these thermodynamic limits, then it suggests that there might be an ultimate limit to the amount of computation that can occur within it.
So even the universe's computational power isn't infinite. There's a cap on how much processing it can do.
That's a possibility, though it's hard to even fathom what such a limit would look like or what its implications might be. It's at the very edge of our current understanding.
It's mind-boggling to think that something as vast as the universe might be subject to the same fundamental constraints as our little computers down here on Earth.
It is, and it underscores the interconnectedness of everything. We often think of information as something separate from the physical world, but this perspective suggests that information is deeply intertwined with the fabric of reality itself.
It's almost as if information is a fundamental ingredient of the universe.
Yeah.
Just like matter and energy.
Exactly, and that realization has the potential to revolutionize our understanding of everything from the origins of the universe to the nature of consciousness.
This has been an incredible deep dive. We've gone from our everyday experience with heat and energy to pondering the universe as a giant information processor. What are some of the key takeaways you hope listeners will walk away with?
Well, I think the most important takeaway is that there's a profound beauty and interconnectedness to the laws that govern the universe. From the simple act of your coffee cooling down to the grand evolution of stars and galaxies, everything is ultimately playing by the same set of rules.
And those rules, as we've explored, hint at something even deeper. The interplay of energy, entropy, and information as the fundamental forces shaping the cosmos.
Precisely. Who knows what other mysteries and wonders await us as we continue to unravel this tapestry? Perhaps one day we'll even crack the code of the universe's operating system and unlock the secrets of its grand computation.
Well, that's a thought to leave our listeners pondering. It's been an absolutely mind-expanding journey, and I encourage everyone to keep exploring the fascinating world of science and the endless wonders it reveals.
Absolutely. Keep those brains firing and never stop being curious about the universe and its intricate workings.
And on that note, we'll bid you farewell from the deep dive. Until next time, keep diving deep.